Good morning. Hi, everyone. 안녕하세요. We're here to wrap up chapter 6 about online algorithms, the design and the analysis of online algorithms. We've discussed the ski rental problem. We've devised and analyzed a simple algorithm, the break-even algorithm, and we've discussed online paging. We've designed and analyzed two popular algorithms, the least recently used algorithm and the least frequently used algorithm. So let's briefly recall a least frequently used algorithm. When the cache is full, well, all pages are occupied, but the user program tries to access a new page. Which page should be evicted from the cache? Well, ideally, a page should be evicted if it's not going to be used in the future in a long time. Because if it is going to be used in the future soon, then we better keep it in the cache, right? To save for another cache miss, another page fault. But we cannot predict to the future, at least our online algorithm cannot. Our optimal offline algorithm can do that. And in competitive analysis, this is exactly the comparison we perform. The current online algorithm is compared to an optimal omniscient offline algorithm. But the LRU algorithm, this online algorithm, chooses the following heuristical strategy. Evict the page which has least recently been used. So looking into the past, that's something that an online algorithm can do. Cannot look into the future, but the past has been recorded. Whenever a page has been accessed, a timestamp is attached to it, and the page that has for the longest time has not been used, that's maybe arguably, intuitively, most likely also to not be used in the future. That's a heuristic, and in computer science, our goal is to make these heuristics rigorous, to provide them with a rigorous analysis, and this is exactly what we have done. We have proven that least recently used strategy for online paging is k competitive. That means it is at most k times worse. It incurs at most k times as many page faults as does the optimal offline algorithm, which can look into the future. And in order to prove that, we've performed the following analysis. We've subdivided a hypothetical execution of some user program, a sequence of accesses, A, of accesses to the different memory pages performed by the user program. We've subdivided that into phases. And in such a way that in each phase, except for possibly the very first phase, the LRU algorithm incurs precisely k page faults. And then we have proven that the optimal, actually any offline algorithm, any algorithm at all, must incur at least one page fault in each of these phases. So that in each of these phases, there's a ratio of factor k, a competitive ratio. The LRU algorithm incurs at most k times as many page faults as does any other algorithm, which incurs at least one page fault. If we could show that in each phase, the optimal offline algorithm incurs at least two page faults, then that means that the least recently used algorithm is k by over 2 competitive. It only incurs k over 2 as many page faults. But this is in general not true. So the only thing, the best thing we can prove is that for each phase where the LRU incurs k page faults, any algorithm, and in particular the optimal omniscient offline algorithm, will incur at least one page fault, thus giving rise to this factor of k competitive ratio. And we've proven that by considering three possible cases in each of these phases, in each of these rounds. Namely, we proved by considering all possible cases with three cases, and we've proven that they cover all possible cases, that the user program must access at least k plus 1 different pages in each of these rounds. And since the cache has size k, no algorithm, including the optimal omniscient offline algorithm, can avoid suffering a page fault among these k plus 1 different pages being accessed. And the three cases we've considered were the following. First case, all the k page faults incurred by LRU in the current round are referred to different pages, which means we already have k different pages having been accessed. And then we consider in addition the last page accessed before the current round starts. And this gives rise to two possible cases. First case, the page last accessed before the current round starts is different from all the k pages that incur page faults in the current round. Then we have k plus 1 different pages and we're done. Right? This case is covered. The next case is when there are at least two different uh, occurrences of the same page incurring a page fault, which means a page gets accessed the first time and incurs a page fault first time. Then some further computation, some further accesses happen, some further maybe page faults occur. But then again, the same page gets accessed again, and again it incurs a page fault, which means that in between those two times that the page is accessed and both time creates a page fault, the page must have been evicted from the cache, and it can only have been evicted from the cache if there were at least k other different pages being accessed, again yielding a total of k plus 1 distinct pages being accessed, which is what we want to prove for the current round. So this is the second case covered. And the third case is kind of resuming our first case, namely the case where we have k distinct pages being accessed and causing faults in the round, and the last page accessed before the current round is equal to one of these pages that incur page faults in the round. And then the same argument applies again. If this page has been evicted, and it must have been evicted in order to suffer another page fault during the round, then in between at least k other pages must have been accessed, and together with the current page, that makes k plus 1 different pages being accessed. And these are all possible cases. This cover all possible scenarios, and in each the user program will prove to access k plus 1 pages, and therefore in each round any algorithm, including the optimal omniscient offline algorithm, must suffer at least one page fault, so that the total number of page faults is at most k times larger for LRU than any other algorithm, and that proves the competitive ratio. So this is a kind of our recap from the last lecture, and we've also analyzed least frequently used strategy, where the decision which page to evict is not based on the timestamp when it was used, but depending on a counter how often it was used. And again, this is easy for an caching algorithm to maintain such a counter, and then choose page to be evicted depending on which one has the smallest counter value. This is the least frequently used page. But we've also proven that this heuristic, which maybe also seems reasonable, is worse, much worse than least recently used. Namely, we've proved that this has no finite competitive ratio. So it's not k competitive. It's not even 2 to the k competitive, so exponentially bad. It's even worse than that. it has no finite competitive ratio at all, right? So we all know that exponential is bad, but this is not even exponential. This is not at all bounded. And in order to prove that, we've constructed maybe artificial, but anyway, we've proven that there exists a sequence of accesses performed by a user program such that the least frequently used strategy incurs any larger number, a factor of m more page faults than the omniscient optimal offline algorithm, which can predict the future. And this is the sequence we've constructed. First, we've kind of made the program access pages 2 to k, so that's k minus 1 pages, and we've made the sequence in such a way that these pages are accessed all the time over, such that the least frequently used algorithm creates a very high access count for all of these pages, while the access count for pages 1 and for pages k plus 1 remain 0, which means that now when in the second part any of these pages 1 or k plus 1 get accessed, the original pages 2 to k will not be evicted because they have accumulated such a high access count. They have been used very frequently and therefore will not be evicted. And this causes a lot of page faults when alternating between accessing page number 1 and page number k plus 1, page number 1, page number k plus 1, and so on. And this is this kind of illustrates the disadvantage of this LFU strategy. Anything that has happened in a long time ago will still affect future decisions, whereas least recently used is really truly temporal locality algorithm. It looks at when the page has been used in the last time, not how often. And the thing is with this current counterexample sequence, an optimal omniscient offline algorithm knows the sequence in advance. It can look into the future and it can see that in the future pages 1 and k plus 1 will be accessed repeatedly, whereas none of the pages 2 to k will be accessed, and therefore the optimal offline algorithm will indeed evict any page numbered 2 to k in order to prevent pages number k and k plus 1 to ever again cause a page fault, whereas the online algorithm cannot predict the future. It is bound to its least frequently used strategy, and therefore it will keep in memory pages number k plus to k, number 2 to k, although these will never be used again as we and as the omniscient optimal algorithm knows. So that the competitive ratio here in this, here we are, right, in this example is kind of like m, right? And we can choose m arbitrary by making the sequence arbitrarily long. So that's a LFU strategy we recalled. And then we've also proven that the least recently used strategy is actually optimal. We've shown that any deterministic online algorithm must have competitive ratio at least k. Okay, so and again to this end, we've considered an optimal online algorithm, and we've performed some hypothetical thought experiment execution of that algorithm on a sequence, and we reconstruct that sequence on the fly as we keep simulating the algorithm. Then we would make we are the adversary, right? This is the adversary kind of argument. We always make the user program or the sequence access in the next step a page which is currently not in the cache. In this way, forcing any deterministic online algorithm to suffer page fault in every single access, right? And of course, this is a maybe a unrealistic scenario. A user program you generally cannot predict how caching algorithm works, but in our analysis, we can do that. That's we call this adversarial technique of proving of proofs in analysis of online algorithms. Now that's only half of the part of the proof of optimality, namely the part that refers to the online algorithm. Now we have to compare that with how an optimal offline algorithm can perform on this or in any sequence. And the thing is that an optimal offline algorithm, which is omniscient, which can know the sequence in advance, can always choose a page to evict from the cache, which is not going to be accessed in the next k-1 steps. Let me repeat that. So we consider an optimal offline algorithm for actually any, and in particular for this access sequence we as adversary have just created. And the offline algorithm being omniscient can look into the future and can make sure that when a page fault occurs here, right? So the current content of the cache here uh, does not include page number A1, right? But the user program accesses page number A1, so page fault occurs, and then an optimal offline algorithm will look into the future. It's psychic, right? And look at the next k-1 pages that will be accessed in the future. And the current cache contents is k pages, k different pages. The future holds k-1 pages. That means at least one of the k pages in the cache currently will not be accessed in the near future, will not be among the k-1 accesses in the future, coming up in the future series of access patterns. And this is, of course, the best choice for a page to evict, the page which will not be accessed in the near future in the next k-1 steps. And this is exactly the page that an optimal offline algorithm will never evict, whichever pages of these is. Once it's already suffered a page fault, it will make sure once it is forced to load new page A1 into its cache, it makes sure that the next page fault will only occur after another k-1 accesses, so that a page fault will incur only in total on every kth earliest and every kth access, so that this is factor k times less than the number of page faults incurred by the online algorithm, right? So the online algorithm, the construction of our sequence, suffers a page fault on every single access, whereas a psychic offline algorithm can make sure to suffer a page fault only at, at most on every kth access, so that the ratio, the factor between both on every access and on every kth access, that's exactly a factor of k, and no deterministic of online algorithm can beat that by construction of our sequence. Okay, so that's a recap of the proof of optimality of k competitiveness in online paging, and in particular optimality of the least recently used strategy. And now this is the final slide of chapter 6. We're going to consider randomized online algorithms, that combine the two paradigms we have seen in the current and in the previous chapter. Previous chapter was about randomized algorithm and their design and analysis, and in particular the expected case performance when we talk about, for instance, Monte Carlo algorithm, right? Monte Carlo algorithms, though, were about decision problems. Here we're not talking about decision problems, but anyway, we're going to employ randomization and expected case analysis for an online problem, namely for the ski rental problem, and surprisingly, it will turn out that a randomized algorithm can do better than the break-even algorithm. And although we've proved that break-even algorithm is optimal, so this is kind of surprising. But the thing is, this is a demonstration of the power of randomization. Namely, kind of by randomization, an algorithm can beat an adversary. Adversary tries, remember how we constructed this worst case sequence here for the online paging, any online paging algorithm. We've constructed a sequence that forces the algorithm into a page fault in every single access because we were the adversary. We knew, we know the current content, we know what the algorithm will do, and we can construct our input in such a way that the algorithm kind of suffers every time. But if the algorithm performs randomization, if the algorithm makes coin flips based on their decisions, then we as the adversary cannot take into account the outcome of the coin flip. They're random also to us, right? And this is basically the idea why randomized competitive algorithms can in general be provably give a better performance, at least from the perspective of competitive ratio, than deterministic algorithm, which is kind of a little bit different from the classical situation where, for instance, randomized algorithms are not known to perform better in the rigorous sense, provably better than deterministic algorithm. There was some evidence for that, right? Remember we talked about the randomized polynomial identity test algorithm, um, but it's not having been has not been proven. Here, on the other hand, we will prove that there's a randomized algorithm for online ski rental that provably performs better, achieves a competitive ratio strictly smaller than 2, which beats the optimal deterministic online algorithm, namely which beats the break-even algorithm. So to see how a randomized algorithm can be that, remember how we've proven the break-even algorithm to be optimal. We have considered any other online algorithm for ski rental, simulated it on an apparently unboundedly long season to determine how many days this specific arbitrary but fixed deterministic online algorithm chooses to rent before switching to buying on an apparently infinitely long sequence. And then we've run that hypothetical algorithm again. And then we've changed the scenario, the input sequence of weather data, so that just when the algorithm decides to buy, then we terminate the sequence, thus forcing it into a kind of terrible situation, a worst case scenario, but after all, we are the adversaries. However, for randomized algorithm, when restarting this algorithm, a randomized algorithm could behave differently, right? So that's the point where our argument of optimality really relies on the algorithm under consideration to be deterministic. You must make sure that when the algorithm is restarted with the same input data, the same sequence of weather data, it will perform the same way, and then we can force it into such a double bind situation. However, when the algorithm employs randomization, this argument does not work, and actually the claim becomes wrong. So this is our randomized algorithm for the ski rental problem. And intuitively, the thing is, when the season is very long, then it makes sense for the algorithm to make a purchase as soon as possible, right? For every day earlier that it makes the purchase, it can save $1 for rental, right? But the algorithm does not know how long the sequence is. So what a randomized ski rental algorithm is, it will determine whether the season is long or short by a coin flip. It will make a bet based on the outcome of a coin flip. If the coin shows up head, then the algorithm will guess or hope that the season is short, and therefore use the break-even algorithm, which is good for short seasons. But for long seasons, it's better to buy early, and this is exactly what we're going to do with when the coin flip comes out tail. Then we'll suppose that the season does not last for D days. It's a shorter season, and therefore it will run for 2/3 times the number of days, and then make a purchase. So remember, the break-even algorithm will run for D days, well, technically for D minus 1 days to be precise, and then on the Dth day it makes a purchase. But let me on this slide be a little bit generous and ignore this plus minus 1, because we're interested in asymptotics anyway. So uh, roughly speaking, break-even algorithm will run for D days, and if the season is still going on, then it will make a purchase. Whereas in the second case, when the coin shows up tail, then it will already rent on the 2/3 times D day. So it will make a purchase earlier. And the factor 2/3 times D, it's kind of an arbitrary factor, right? But the baseline is we want the algorithm, when the coin flip outcome is tail, then we want the algorithm to make a purchase earlier. And this is what happens here, factor 2/3 earlier. Now let's analyze the expected competitive ratio of this randomized online algorithm. So combining, as I said, two paradigms. And in order to determine the competitive ratio, we need to consider the two possible cases that the algorithm coin flip comes up head or comes up tail. That's the only kind of randomized choice that the algorithm makes, just one coin flip. And in the former case, what is the cost? Well, uh, again, we have to consider three cases about the length of the season. So if the season is long, if the season lasts for at least 3 days, then if the coin flip has come up head, then the algorithm will execute the break-even algorithm. That means it will run for D minus 1 days and make a purchase on the Dth day. And I'm going to be a little bit less rigorous and ignore this minus 1. I'm just going to say the algorithm will incur a cost of 2 times D. D for the first D days, and then another D for the D plus first day where it has made the purchase. If the coin flip comes up head. If the coin flip comes up tail, then the algorithm will do the following. It will rent for 2/3 times D days, and then make a purchase which incurs another D dollars. So total number of dollars spent in this case will be 2/3 times D plus D, which is exactly this quantity, right? In the case that the season lasts longer than D day, so that in both cases the algorithm really comes to the point where it decides to switch to buying. Here it decides that earlier, here it decides that later. Now the expected cost is the cost incurred in both cases weighted with the probability of each case. But since we consider fair coin, these probabilities are 1/2. So, and if you now do the math, the total expected cost is 11/6 times D. And so the competitive ratio, let's compare this case where the sequence is very long, longer than D. The optimal offline algorithm will know that in advance and therefore will make a purchase on the very same day and therefore on the very first day and therefore will incur cost of D, no rental at all, so that the expected cost in this long season case for a randomized ski rental algorithm is a factor of 11/6 larger than the cost of an optimal offline algorithm. So the competitive ratio in this case is 11/6, and observe that this is really strictly less than the factor of 2, actually 2 minus 1/d, we have proven for the deterministic break-even algorithm. But this is only one of the cases. So now let's consider the next case, the case where the length of the season is somewhere between 2/3 D and D. Okay, so this is a case where the season is long, at least as long as D, where both parts of the algorithm, the head and the tail part, eventually decide to make a purchase. In the second case, the algorithm decides to make a purchase only in one of the two cases, namely when the break-even algorithm is invoked, when the coin comes up head, then the algorithm, our randomized algorithm, uh, will never switch to buying because the season is too short. Remember, break-even algorithm only buys when the season has length at least D, but this is once the previous case. In this case, it will never get that far, the break-even algorithm, and therefore will keep on renting. For how many days? Well, for L days, that's all length of the season in the second case. Whereas if the break-even algorithm is not executed, if the coin flip comes up tail, then the algorithm will eventually switch to making purchase because the length of the season is at least 2/3D. So after 2/3D days, our algorithm will make a purchase and thereby have incurred the same cost as in the first case, 2/3D for having rented for that long and then making a purchase another D. So let's now determine the competitive ratio in the second case, expected competitive ratio. So it's both again weighted with a factor 50/50 for the coin flips. But now we need to compare this actual cost to the cost incurred by the optimal offline algorithm. And what is the cost incurred by the optimal offline algorithm? The optimal offline algorithm knows, the psychic, omniscient, can tell that the length of the sequence of the season is something like this. And here, the optimal offline algorithm will never make a purchase, right? Because the length of the sequence is less than D. So the cost will be L dollars for renting, which is less than D dollars for making a purchase. So that the optimal offline algorithm will incur L dollars in this case. And now we need to compare the actual expected cost to the cost of this L of this optimal offline algorithm. And in order to do that, we're going to replace D here with L, actually with 1/2 times L, this quantity, because of this inequality, right? So if 2/3D is less than L, then that means D is less than 3/2L, right? 3/2L, and that's exactly the estimate we apply here. We replace D with 3/2L, and then we can factor L. It's just numbers remaining here, and right. So yeah, and then there's third case where the sequence is even too short for even the tail. When tail came up, that algorithm to ever make a purchase, then even in the first case, the sequence is so small, so short, less length than 2/3D, so that the algorithm will not make a purchase in this case either. So that the expected cost in this case is L, which is equal to the actual cost incurred by the optimal offline algorithm. So here we have competitive ratio 1. Here we have, if you do the math, competitive ratio 1.866 or something, right? Which is less than 2. And in this case, we have a competitive ratio. You do the math, the calculations, 1.75, or predictably, that's 7/4, which again is strictly less than 1/2. So to summarize, The randomized ski rental algorithm has a competitive ratio of 1.833. Sorry, yes, 1.833333. This dominates this one, so this is going to determine the competitive rate. And this is better than the 2 minus 1 over d competitiveness of the of any deterministic online algorithm. So to summarize, randomization can beat deterministic algorithms at least, probably at least in this competitive ratio setting. Okay, so randomization can beat an adversary. That's basically the gist. And how did we prove that break-even algorithm is optimal? We've constructed for an arbitrary but fixed deterministic algorithm A this adversary, that worst case sequence, and we've constructed that by running that algorithm hypothetically as a thought experiment and analyzed how it behaves. And then we've constructed the sequence to kind of beat that behavior. This is how to say, if you're playing poker and you know that your opponent has a tendency to uh, uh, bluff, then you may try to call the bluff. Whereas if you know that your opponent will never bluff, then you trust his or her bets, right? So that's basically the same here. Here, we in our analysis know the behavior of the algorithm. Well, we determine the behavior of the algorithm on one explicit sequence, namely the sequence that has skiing weather all the time, in order to determine how it will behave, and we capture that behavior into one number x. That's the number of the days that this algorithm rents before making a purchase, and then we execute that algorithm again. And being a deterministic algorithm, we can predict that it will perform the same way as previously, at least as long as the sequence of weather data remains the same. Namely, for the first x days, we make our sequence of weather to be skiing weather. And on the x plus first day, when the algorithm again switches to making a purchase because it's deterministic, it will do the same as with the infinite long skiing season. But then we change our mind, then we change the sequence of weather to switch to bad weather for skiing. And in this way, we've kind of fooled the algorithm. We've created artificially a bad sequence, input sequence, but we as adversaries have been able to do that only because when the algorithm is supposed to be deterministic, and therefore because we know that it will behave the same way again when we restart it on the second sequence of weather data that initially looks the same but eventually makes this difference. So that's really why we as adversary in this kind of proof need to rely and depend on the algorithm being deterministic one. Whereas if the algorithm is involves some randomization, then if we restart it, it could behave in a different way, and our entire argument in this proof breaks down. And this is exactly demonstrated that with this randomized algorithm, the randomized algorithm achieves a strictly better competitive ratio in expectation than the optimal deterministic algorithm. Great. Okay, so so we've discussed the ski rental problem. We've discussed the break-even algorithm, which is a very simple algorithm. We've analyzed it, thus turning it from a heuristic into an actual algorithm. We've proven that it is too competitive, 2 minus 1 over d, Right, I should say that. So here we always only say that it's roughly, approximately, because there's this -1. I've been generous, too generous about this -1 in the analysis. Um, and I encourage you to make this more rigorous by really making a more careful analysis that takes into account this -1. For now, it suffices that asymptotically, as d tends to infinity, as d becomes large, then this -1 doesn't really matter. So for sufficiently large d, the competitive ratio is 1.833 and 1.75. Maybe it's a little bit different numbers when taking into account this -1, the fact that the break-even algorithm makes a purchase not after d days, but after d-1 days. And that leads me to another important point. How do you learn, uh, how do you recap and uh, learn from this lecture? I encourage you not to memorize the slides. That's not the point of the slides. Um, Instead, let me recommend that, for instance, you could look up the different chapters in Wikipedia. This is standard material in computer science. There are very good Wikipedia pages on these topics. Then there are, of course, the standard textbook we recommend for this course, the Introduction to Algorithms, the MIT book, right? But most importantly, please do the calculations by yourself. So some of the calculations I perform here online on the slides. Sometimes calculations are deferred for homework or different, but you really learn only if you do the calculations by yourself. I'm not interested in checking the facts that you're able to reproduce the slide contents. That's not the purpose of learning, right? Any memory stick can do that much better than a human memorizing, right? But the goal of this lecture is to convey understanding, and understanding is the second level in the Bloom hierarchy of cognitive learning. Knowledge is the ground level. I trust you can acquire knowledge. You've been trained to acquire knowledge throughout your school and high school and university life, but here really aim for the second and third level of Bloom's hierarchy, understanding and being able to apply what you've learned to new situations. So please do that maybe by redoing the calculations by yourself, and we make homeworks that really go beyond reproducing knowledge. So that's my recommendation for learning. And to wrap up this chapter 6, so we've considered ski rental problem, break-even algorithm. We've analyzed it, shown that it is too competitive, and we've shown that this is basically optimal. More precisely, we have shown that 2 minus 1 over d competitive and 2 minus 1 over d is optimal for any deterministic online algorithm. And we've proven that using this adversary argument technique by constructing for an arbitrary but fixed deterministic online algorithm a sequence where it cannot be the competitive ratio 2 minus 1 over d. Then we've considered the online paging problem for managing a cache. We've considered the least recently used heuristic, and we've turned this into an algorithm by analyzing it, by showing that it is actually k competitive, where k is a size of the cache. So it cannot perform worse than, in the worst case, it performs k, it incurs k times more page faults than a omniscient, psychic, optimal offline algorithm that is able to look into the future, which page the user will access in the next k steps. And we're seeing that maybe equally reasonable heuristic of least frequently used is not competitive at all. It has no bounded competitive ratio. And we've proven that by, again, constructing a bad input sequence, which is bad for an least frequently used, but which an optimal offline algorithm can achieve a good, a small number of cage faults, and therefore the ratio will become arbitrarily large, which means it is not competitive in any sense. And then we've proven that this least recently used strategy is actually optimal among all deterministic online algorithms, again, using a adversarial construction for a sequence where LRU, or actually any deterministic online algorithm, cannot beat the factor k of incurring k times more page faults than an omniscient offline algorithm. Finally, we've considered randomized online algorithms and the expected competitiveness. So when we have randomized algorithm, then of course the competitive ratio becomes a random variable, not a number, but a variable. And we've constructed a simple randomized algorithm, which is a hybrid of two versions of the break-even algorithm. If the coin flip comes out head, then it just executes break-even algorithm. If the coin flip comes out tail, then it performs break-even, but with a reduced price. That's one different way of looking at things. Reduced price of 2/3 times the further cost of making a purchase. And we've shown that this algorithm has a strictly smaller competitive ratio than the deterministic one, namely it is 1.84 competitive. And I encourage you actually to design, analyze a better, even better randomized algorithm for the online ski rental problem. So if you look at this algorithm and its analysis, you will see that the number 2/3 times d is kind of arbitrary, right? Why did I make the algorithm rent for 2/3 times d days? Also observe that there's a kind of imbalance. In the first case, the competitive ratio is a little bit larger than in the second case. And in the third case, it's even 1, so that's actually best possible anyway, right? So there are two ways of improving this. One by changing the factor 2/3 to something different. And the question is to what? And another improvement is by changing maybe the probabilities, right? Replace a fair coin by another coin, which kind of decreases the competitive ratio here at the expense of increasing the competitive ratio here, and trying to make both competitive ratios equal. Then the worst case competitive ratio in all three cases will be the same, but better than this. So there's various ways of improving it, and I think we're going to post that as a homework problem. So this is the end of chapter 6, online algorithms and competitive analysis.